Hey there, everyone. Ryan Schul here. Welcome to my channel. The project today, I want to talk about how to measure clustering performance. When we're working with things in the regression world, we have evaluation metrics like R squared, adjusted R squared, RMSE, mean square error, things like that, right? That will show us how accurate the model is performing based on the training set and the testing set, right? The testing is the holdout set, and you compare, or the model makes its evaluations. You compare what the model comes up with to the actual holdout set, which the model hasn't seen, right? So the model can't see the data and memorize it. So in the classification side, we have F1 score, accuracy, precision, recall, things like this. A lot of this is based on the relationships between true positive, true negative, false positive, false negative, right? And the combination of those, that's how you determine those metrics, right? And in clustering world, we don't have those things. Clustering is unsupervised. So when you make a cluster, how do you know that cluster is accurate? Okay, that's the question. You don't really know, right? How do you know if it's correct? You don't really know, right? You don't know that. You just run it, you get the output, and you just assume that is right for the most part, right? But today I want to talk about a few different methodologies that we can actually employ to see how accurate these clusters are being created, okay? So this is kind of like an evaluation of the performance of the clustering algorithm, okay? So let me take you through it. I think this is pretty fascinating, pretty interesting. I've been in the data science world for 12 years. I don't think I've actually seen anybody ever do this, but I was curious myself, so I started to do some research to see how this is done if you want to do it. Now, again, like in the clustering business, like you can just set it and pretty much forget it. You know that it's working. You know that's probably pretty close, probably pretty accurate. But today I want to prove like how to determine the accuracy of these outcomes, okay? So again, like unlike supervised models, any kind of clustering where it just focus on k-means. There's a bunch of clustering algorithms. I already have a video on that. I put that out almost a year ago. There's a whole bunch of clustering algorithms. I don't want to talk about all those. I want to talk about just one, and then understand the metrics or the true predictive labels that directly measure the accuracy, like we have with classification and with regression, right? And there's multiple ways to achieve this type of performance or these actual quantifiable metrics, right? So just to give you a quick heads up, we're going to look at a silhouette score. Basically, this measures how close each point is to its cluster versus other clusters. Okay, so good value, closer to 1 is better. Davies-Bouldin Index, the DBI, is a ratio of intra-cluster to intercluster distances. Lower is better, right? So if everything is clustered tightly together, that's good. If the clusters are kind of like, and k-means they don't overlap by definition, they can't. But in some clustering techniques, if it's close to overlapping or kind of bumping up against the neighbor, that's not so good, right? You want tight, nice, crisp clusters. Calinski-Harabasz Score, CHI, is the ratio between cluster variance and within cluster variance. So kind of similar to this. Higher is better, but this is like this is the other way around. So lower is better for the DBI. For the CHI, higher is better. The adjusted RAND index, how well predicted clusters match the known labels. Okay, if you don't have the label, you have to create it. If you have it, great. If you don't, we'll create it. In this case, I didn't have it in the default data set, so I created it. I'll show you how to do that. 1 is perfect. Higher is better. Closer to 1 is better. Lower is not quite as good. And cluster accuracy, this is the alignment with known labels after the best label permutation. Okay, so greater than 0.7 is good. These are the sort of like the benchmarks that we're going to look at. So I'm going to go ahead and download dbcars. This is a canonical classical data set that I've used for years. A lot of people start their data science career just looking at this stuff. It's great for regression, classification, and in this case, clustering. Okay, so I downloaded the data. So we have everything in this data frame right here. This is called mtcars. We're looking by default at the head of the data set, looking at the top five records right here. So I'm going to go ahead and standardize or scale. Standardization is very important for clustering. It makes everything on the same relative basis. If you have huge outliers that drag your clustering over to one end or over to another end or up or down or all over the place, that's not so good. You want to take everything and basically normalize it or scale it or standardize it. There are slight differences between these techniques. I have a video on that. You can check that out, right? We're just going to standardize or scale everything in this case. So basically bring everything to the same relative normal scale, almost like a log scale. If you take a log normal distribution of a stock price, and the stock price has big tails or can deviate very high and very low, and there's a lot of deviation or standard deviation or variance. This will take everything and make it just more normalized, right? So that's what that does. So I'm going to go ahead and normalize the data and then create a column called cluster based on this normalized or standardized data. Okay, so here's the original data set. We start with miles per gallon cylinders, displacement of the engine, end with AM, gear, and carburetor. And again, we have AM, gear, carburetor at the end, and cluster is the new column that we just created and appended onto the original data frame. So this car goes into cluster 2, this one goes into cluster 2, this is 0, 1, 1, and so on and so forth. So let's create a scatter plot here so we can visualize it. I always say a picture is worth 1,000 words. When we look at the clusters here, we can see the PCA is principal component analysis. 1 and 2 go over here. These are cluster 2s. These are cluster 1s, and this is cluster 0, and this is cluster 1. So you can see basically how this works, right? So the 2s are kind of in the northwest a little bit, kind of around the middle of the line a little bit, but enough like it's higher and over to the left. All these cluster 1s are pretty much on the left and kind of like lower, almost southwest quadrant. Couple kind of get scattered over here a little bit, and then for the most part, cluster 0 and sort of like on the East Coast. If you imagine the map of the United States, cluster 0 is the East Coast, cluster 2 is kind of like Pacific Northwest, getting down into, I guess, maybe Colorado or something over here. And then these guys down here, cluster 1 is kind of Southwest, Arizona, New Mexico, California. Okay, if you imagine the geographical map. So like I said, I have to create the label here just so I have something to make a comparison to for my adjusted RAND index. So the ARI needs some type of label to match the performance to, right? So we can create that, and there's nothing wrong with that. It doesn't come by default, so we'll just create it on the fly here, okay? So if horsepower is less than 100, we're going to say low. If less than 50, medium, otherwise high. So this is going to be low. Horsepower right here is 93. It's under 100. This is 110. This is medium. This is high. This is 175 because it is over 150. Okay, so hopefully that makes sense. We're just creating labeled data because all we have over here is all numerics. If you look at this, this is all numerical data, but we need some type of non-numeric data, some type of labeled data, which we just created. Okay, so hopefully that makes sense. So we run the ARI, adjusted RAND index, and we get 4.60. So this ARI basically looks at all the labels and then matches that to the how efficient these clusters have been created over here. So you look at the cluster over here, that was the first step. Now we have the label over here. The ARI is taking everything from the label, a true label encoded. This is right here. And this comes from here. So mtcars is the data frame. This is the column number cluster. And then this true label is also in the data frame. So the ARI is 0.46. Basically, anything that's 1 is perfect match. 8 to 1 is excellent. 5 to 8 is good agreement. We have almost 5.0 or 0.5, almost 0.5. We actually have between 3 and 5. This is moderate agreement. So useful insight, but not perfect. Okay, so the clustering could be a little bit better. So that tells me probably k-means either number 1 isn't the best way to cluster this data, and there's a bunch of different clustering techniques. There's agglomerative, there's db scan. I can guarantee that won't work in this case. That's density based, right? But there's optic clusters, affinity propagation is another one, hierarchical clustering. There's a bunch of them, right? So we can try different clusters and then rerun the ARI and see if some perform better. But I would hypothesize, I did not do this, guys. I'll admit, a little bit lazy. I was just a little bit lazy. I just took everything from mtcars, which is everything right here, and scaled that. Now, this is just the whole universe of data that's been scaled. If I just looked at the miles per gallon, cluster, and displacement and horsepower, now these are highly correlated features in a data set. The more miles per gallon, the smaller the car, the smaller the displacement, and the less horsepower, guaranteed. Okay, as you get fewer and fewer miles per gallon, like a sports car, the bigger the cylinders, or more cylinders, you have a 6 or 8, the greater the displacement and the greater the horsepower, right? So As cylinders displacement horsepower increase, miles per gallon decrease, and vice versa. If I just clustered those, we would probably have tighter clustering and better fit. I'll admit, guys, I was lazy. I just took everything, but I could easily take just these three features right here and cluster those, and we'd probably have a higher ARI. But again, if that didn't work, we could go back and fit or pick another clustering algorithm and try that. So when I just did the k-means, everything worked out, right? I'm looking at this. Yeah, this is clustered. This is done, guys. This job is done. Deal with any done. Go ahead and sign off on it. But actually, the clusters are okay according to ARI. We're getting up down here. Moderate agreement, useful insights, but not perfect. So this could be better. This could be better, right? And my objective here is not to make it better today. I really don't care. I'm just taking you through clustering performance. That's what I want to show you. And maybe I could, add something to the data and refine it and make it better. Again, that's not the goal today. That's not what I'm here to do. I'm just evaluating different quantitative clustering performance techniques. That's what I'm trying to do. So that would mean, I guess, try different algo or just focus on do a regression analysis. I'm sorry, do a what is it called? Correlation analysis and see which are the highest correlated features, and then just do clustering on that, and I'm pretty sure that's going to fix the problem. Okay. So anyways, let's look at the different technique, accuracy via label mapping. This is Hungarian algorithm. When I run that, control enter to run, I get 0.719. So you can see what's doing in there. Again, looking at the true label encoding and the k-means labels, just to see how accurate this is. So an accuracy of about 72%, 72% of the cars were correctly grouped to their true cluster. But again, like 30% are kind of like getting arranged into the wrong cluster or getting organized or moved into the wrong cluster for whatever reason. Again, I didn't pick the highest correlated columns. I picked everything. I just dumped it into the blender and hit mix. That's all I did. So if I take a step back and really refactor this just a little bit and make it more accurate and more refined, I think the outcome is going to be better. Maybe I'll do another video on that. I don't think so. I mean, I think like I explained the issue, and you could do that for yourself if you're motivated to do that. And if not, then that's fine too, right? Okay, so another technique to quantify how well the clustering is being done is called silhouette score. So I can go ahead and run this. I see 0.405, so this is the breakdown. 0.71, strong clustering structure. 5 to 7, reasonable structure. We fall into this band right here, 0.26 to 0.5. Moderate structure, some overlap between clusters. So these clusters are actually getting kind of like mixed together a little bit. Now, the k-means actually doesn't allow clusters to be overlapped. If you look at the chart over here, none of these are overlapping, right? They're all in their separate clusters right here. This kind of comes close to an overlap, I would say, cluster 2 and cluster 0. But again, these are separate and distinct. The cluster 0 is kind of swept off to the right. 0 or 2 rather is kind of like northwest, Pacific Northwest. This is kind of like southwest down here. And these kind of bump up on cluster 0. So these almost could be cluster 0, I think, but they're actually getting kicked into 1. And this could almost be cluster 0, but this is getting picked up by 2. So I think that's what this this metric is telling us. 0.405 is pretty good, but you know what? It could probably be a little bit better, okay? But that's fine. We'll live with it. We'll live with it. So Davies-Bouldin Index. So when I hit this, again, higher is better. This shows us that each compact cluster is looking at the intra-cluster distance. So this is looking at how tight each cluster is with its centroid. This is the middle point of the cluster, and then all the little scatter points around that centroid, right? And how that is packed into one cluster. Look at, we have 3 clusters here, or does it go into another cluster or different, right? Based on how heterogeneous it is, right? Which is different, or how homogeneous it is, which is the same. So anything around 0, excellent clustering. 0.5 to 1.5 is reasonable clustering. That's what we have right here. So we're right in that band. That's reasonable, not perfect, but it's okay. Anything greater than 2, poor clustering. So we're not in that bucket. We're not in trouble. So let me look at the Calinski-Harabasz score. We get 24, and we can actually iterate through a couple different ranges for that. We have 0.27 down to, or 27.12 down to 23.86. So basically, this is showing us anything that we have a 24, right? So this is a moderately good score. The higher, the better. And basically, the interpretation here is the variance ratio that evaluates clustering quantity based on between cluster dispersion. So how tight and how crisp are these clusters segregated among themselves, or are they kind of almost bumping into other clusters? And we saw some evidence of that, right? So these over here on the right are fine. These on the top left are fine. These on the bottom left are fine. There's almost a little overlap between these two right here, the Mazda RX-4 and the Mazda RX-4 WAG, whatever that is. And then this Merc 280 and Merc 280C, like obviously these are going to be similar. These two cars are almost the same. And this Hornet 4Drive and Valiant, these are the same. So again, I think the problem is that these two almost bump into these two, and these two almost bump into these two. So again, the clustering is being done, and it's decent. It's pretty good, but not perfect, right? So that's kind of it in a nutshell, guys. Just wanted to take you through it. Again, I have some notes down here. Adjusted RAND index. That's the first one we saw. This is a supervised technique, and it uses label independent matching. Accuracy, Hungarian. Again, supervised. It uses direct cluster matching. So a score is not supervised, right? So that is an unsupervised algorithm. Cohesion versus separation. Davies-Bouldin Index. This, again, is not supervised. Lower score is better, and Calinski-Harabasz, again, is not supervised, and higher is better in this case, okay? So that's it, guys. That's how to quantify your clusters and how to measure the overall performance of your clustering algorithm. And again, I have another video that talks all about a bunch of different clustering techniques. There's a whole bunch of them out there. I think at least 8, maybe 9, maybe even 10. I'm not sure, but there's at least 8 different ways to do this kind of work, right? So I would say, take a look at that, Google it, talk to ChatGPT to get some more insight on different clustering techniques. I think it's very interesting. That's one of my favorite things in the data science space is clustering. And then again, this is how to evaluate the performance of your clustering algorithm and how to prove that it is outperforming expectations or meeting expectations or maybe only short of expectations. And again, I told you what to do. Pick a different algo if it's coming up short, or pick certain features that you want to cluster together. I did everything. I just dumped it into the blender and hit mix. That's all. Yeah, it's a little bit lazy. I didn't want to parse out the different fields, but I could certainly do that. And you could do that too. I'll leave it up to you to do that. Okay, that's a good homework assignment. So I'm going to wrap up the video right here. Thank you so much for tuning in and for sticking with it to the end. I'm going to wrap it up right here, and I'll see you guys soon when I post the next video. Goodbye for now.